So 610,000 people per year die from cardiovascular disease, and even more people than that suffer from some form of arrhythmia, which can contribute to things like strokes and pulmonary embolisms. Uh, part of the problems with continuously monitoring heart rate to prevent illnesses such as these from occurring are that current devices can often be cumbersome, heavy, difficult to wear, and require to be plugged into some sort of external monitor at all times, which limits the patient's mobility. As a result, our concept was to design a lightweight, compact, portable heart rate monitor that transmits data in real time wirelessly to a computer via Bluetooth. So we are recording ECG signal from between the right and left arms, which corresponds to lead 1 on the traditional Einthoven's triangle. We are running that through a signal amplifier and a high-pass filter in order to eliminate low-frequency noise and to amplify the signal so that it can be read over the standard noise. And then we are sending that through the Arduino board through an HC05 Bluetooth module to the computer, where it is being read in real time in a MATLAB script. Additionally, all of our electronic components are externally powered from two 9-volt batteries, and we also have a variable gain resistor on the amplifier through this potentiometer so that we can turn the signal, we can turn the sensitivity up or down, which will increase or decrease the magnitude of the signal. And that'll take things into account such as an individual's skin conductivity or other personal factors of their ECG signal, so that a wide range of patients will be able to be measured on this and not max out the reading capabilities of our device.
So when we read in the voltage on our Arduino board, our Arduino basically packages that reading into a base 64 2-character message that it would transmit over Bluetooth into our computer, and then from that we do the reverse operation to unpack the signal, and basically that allows for a quicker transmission. And in a continuous loop, it'll just keep reading the signal in, and from that plot the raw data. So this is what we're seeing right now, the raw data. And basically, every 5 seconds or 6 seconds or however long you set the interval, it'll take that past chunk of data, detrend it, filter it, and basically just smooth it so that we can have a more clear ECG signal. And from that, then it'll calculate the heart rate in beats per minute. And then if a certain threshold for the heart rate is met, so basically, like, for example, if you see 200 beats per minute for over 3 periods, so 15 seconds, it'll set out an alert where you would have to shut it off in order to allow it to keep going. And if you don't shut it off, it would theoretically call like 911. And after you finish running this and close the program, you'll have the option to download the data and store it. We've already shown you how when we have Torn plugged in, the computer will be reading his ECG signals. For the sake of now showing you the other features, so we have him plugged in, the code's running, and we've lowered the threshold to 50 beats per minute for 5 seconds total, and Saturn obviously reached this, so now we have an alert generated. So if you say yes, then the signal will continue to be read, and then it looks like we got another alert, and so say we do no, then the program will be like calling 911 theoretically. And then at the very end, now the program's terminated. You could choose to download the data or not. So if we do yes, then we have all this data here that we can use. And that data can also be found in the same directory. And this will be the data file that we get. And so what this simulated signal really shows is that our code is doing a really good job of picking out the heart rate and the actual QRS signal. And it also shows that our circuit itself is also reading the signal and is transmitting it. It's just simply between our two arms and using our own heart rates as a signal, our own ECG signal. That it's been really noisy, and I think that's where most of the improvement going forward can come from.
So, in future iterations of our device, we plan on prioritizing collecting a cleaner signal, which we would need to investigate the electronics and the Bluetooth in more depth. However, if we did have a more clean signal from the human body, it might look something like this. Now, this is some simulated data that a heart rate should look like. And what our program does is, as you can see, we're filtering it out in real time as this simulated data is being entered. And we are looking for things such as heart rate, and theoretically also in future iterations, we could look in really more detail within the EKG signal itself, possibly look at QT intervals to identify things such as long QT syndrome, and we can look at more complicated problems, different kind of arrhythmias, like what seems to be happening right now, and identify those issues and also include alerts that could tell the patient to alert their doctor or something like that. So as you can see, our design poses several advantages over many current devices in that we can record ECG with a small apparatus and transmit the data wirelessly to a personal computer, and then from there we can alert medical professionals if certain issues end up happening. However, there are some limitations of this device that could be addressed in future iterations. Most of the issues that we've been seeing are coming from the electronics. We're seeing, when we're trying to record our signal, we're seeing a lot of noise. And ways that we can improve this are improving the way that we're filtering and amplifying. In addition, maximizing even more so than we currently are the amount of data that we can put through the Bluetooth connection in a limited amount of time. Which we've been doing so far, but we could extend even further in future iterations so that we can get a less undersampled signal. In addition, once we get that cleaner signal, we can go even farther with the computational aspect, perhaps filtering out to identify even more problems other than simply, say, tachycardia or cardiac arrest, which is what we're monitoring for right now. Our concept for the future is to have this as a small device that can be clipped to the user's belt, and the wires can be run up to the two arms, or even in theory the two sides of the chest, whichever one would produce a better signal. So we were going to close this apparatus, the proto board here, and the Arduino into a laser cut box, and then we have a 3D printed belt clip that fits onto the back of the box and clips to the belt nicely, and we've tested it's able to carry the weight of an Arduino. Also, we would need to include the Bluetooth chip, the HDO5 module on the proto board instead of on an external breadboard.